Uh, Today we will discuss the remaining portion of our the topic on photochemistry. So I welcome again all of you for today's class. I plan to do the discussion on Barton reaction, which we had in our first semester maybe. If you can recall, when I was teaching the radical chemistry, there you have been introduced to this reaction. We'll go to another important reaction, which is called as dipymethane rearrangement, and we'll look into the chemistry of arenes. Okay, so let us start the topic. So Barton reaction, actually, this is a reaction which is also known as Barton nitrite ester reaction. Is a photochemical reaction that involves the photolysis of alkyl nitrite to form a gamma nitroso alcohol. Okay, this is the primary product, which is the gamma nitroso alcohol. Okay, the substrate was alkyl nitrite to the product gamma nitroso alcohol. Okay, so this is the reaction, which is being driven by the light energy. Okay, so photon is being used as the reagent here. Now, in this case, what we say is that the homolytic bond cleavage is happening. Okay, homolytic bond cleavage. So you have alkyl nitrite. So the ON bond is generally getting cleaved. Okay, so and homolytic cleavage. So you have by radical formation, one radical will be on oxygen, another is N. So you have nitrosyl oxide, radical will be generated. And after that, what will happen? The gamma hydrogen, sorry, this is the delta. So delta hydrogen abstraction will take place. Now the reaction will take place in a 6-member transition state medium, and in this process, the generation of another alcohol, another radical will be there, and that radical generally is of carbon center radical, which gets recombined with the NO radical, which has been generated at the initial stage. Okay, so in this way you have the formation of nitroso alcohol, and this nitroso alcohol, what happens, this nitroso group which can undergo tautomerization to produce the oxime. Okay, so you have C double bond N, then OH, so that tautomerization will take place. We have, if you have the CH anything, okay, some hydrogen is there, you have NO, okay, and you have R here. So what will happen is you have tautomerization, okay, and that will be producing the oxime. Okay, so that will be producing oxime. Okay. Now, based on this generation, you can have further reactions. Sometimes we'll look into the different examples. Since this is imine, what we can expect is, if you have acid source, it can undergo hydrolysis to produce the, okay, so you have here one more substituents, so produce the corresponding carbonyl compound. So you can have R double bond O. Okay, so that kind of reaction will be finding in this case. Okay, so let us look at the mechanism in a simplest way. So what we find here is that you have the alkyl nitrite. This is the nitrite, this is the alkyl part. So you have alpha, beta, gamma, and delta. So delta hydrogen, okay, you should have. Now if you shine light, what will happen? This bond gets cleaved. Okay, and you have O dot, and here NO dot will be there, NO dot. So O dot can easily abstract the hydrogen to generate this radical. So this radical OH, and here the radical. And since you have NO dot, so now they can recombine, and you have this one which can undergo tautomerization. So you have hydrogen here. So you will have the tautomerization, and you have the oxime formation. Okay, so that is the thing. Now you have to remember one most important point in this particular reaction is that the reaction is highly regioselective. Means uh, the abstractions of hydrogen will take place from the same side of the alkoxy radical. Okay, so alkoxy radical, if it is upward direction, the hydrogen abstraction will be from the upward directional hydrogen. Okay, so you may have the delta carbon having hydrogen of different types. Okay, you may have the delta carbon which is upward or the same directional of the alkoxy radical, or which may not be the same directional of alkoxy radical. Okay, but the abstractions of hydrogen will take place only from the same direction, not the other way. So examples will make it more clear. Let us look at some important uh, examples. Okay, so before that, just let me give you some particular information regarding the what kind of light is required in this case. Okay, the nitride, particularly the alkyl nitride, which we find is that it has the weak absorption. It has the weak absorption band in the region of 320 to 380 nanometer. Okay, so the irradiation using Pyrex filter. So the Pyrex filter, if you use to limit the wavelengths to greater than 300 nanometer, thus avoiding side reactions. So what does it tell is that suppose you are using a light source, so it can generate the different wavelengths of light, maybe below 300 to above 300, whatever it is. Now you can use a Pyrex filter. Okay, and if you have a light source, so if you have a light source, okay, so if you use the Pyrex filter, what its job is, it will cut the light, okay, of below 300 nanometer. Okay, so below 300 nanometer will be cut off. So whatever light is coming here, passing through this filter, will be above 300. Okay, so above 300 nanometer wavelength, that light. And since you have the absorbance of nitride, alkyl nitride is of 320 to 380 nanometer, so above 300 is required, and you can do the reaction very smoothly. But if you have low wavelength, if you don't use the Pyrex filter, what can happen is you may have the side reaction there, because you can have the 254 nanometer or 250 nanometer, 205 nanometer of wavelength, okay, that are more stronger, so you can have a lot of other bonds maybe get cleaved. So that is the purpose of using this Pyrex filter. Now let us look
Sir,
at yes.
Sir, Pyrex means?
This is kind of a material which is, we have the glass. Similarly, we have the Pyrex. Okay, is a transparent glass type. Glass type is looking like a material which is transparent. Light can easily pass through. Okay, you can look into from one side to another side. It is very transparent. A material, we call it the Pyrex. Okay. Similarly, we have the glass.
Okay, sir.
Okay, so glass,
Yes, sir.
it allows the wavelength above 360. Okay, so if you use the glass, what can happen is below 360 will be cut out. Above 360 can pass through. Got it? In Pyrex, generally the 254 nanometer or the below 300 nanometer will be cut out. So only above 300 nanometer will be passed through. It can pass through the Pyrex material. Okay. So
Okay, sir.
yeah, so let us look at the reaction now. Suppose you have a substrate here. Okay, now this substrate doesn't have any nitrite, okay, any nitrite functionality. So you can generate the nitrite functionality. What you use is that nitrosyl chloride you can use in presence of base. So if you have any hydroxy group that can quickly react with nitrosyl chloride, and you can generate the nitrite, corresponding nitrite. So this is the nitrite group has been generated. Okay, so in this case, now you look at this group at what direction? It is upward direction, right? It is upward direction. Now in this particular molecule, if you look at, you have upward directional methyl here, here upward directional methyl. Okay, got it? Now, if you count from this particular oxygen, because when you are irradiating, what is going to happen during irradiation? This NO will come out, you have oxygen centered radical will be generated. Now, this radical will try to take or will abstract the hydrogen from delta carbon. Okay, so if you count from here, alpha, beta, gamma, and that carbon is delta. Okay, similarly you have alpha, beta, gamma, and this is delta. So both methyl are of delta position. Got it? Both methyl are of delta position. So that's why, and both are of upward direction. That's why in this particular substrate, we'll be expecting two different kind of reactions. Okay. So one is, if you use the irradiation, what is going to happen? This oxygen center radical can abstract the hydrogen from this methyl via 6-membered transition state. So there it can generate a radical, okay? And that radical can recombine with the nitrosyl, got it? Recombine with the nitrosyl, and then that can undergo tautomerization to generate the oxime. Okay, so here that oxime formation has taken place. Got it? And now, if you use some dilute acidic condition, what can happen? Suppose you are using acetic acid, okay, a little bit of water. So what you can expect is this oxime can be cleaved to aldehyde because you have hydrogen here. So it will be double bond O, so aldehyde, and that aldehyde and oxygen both are of same direction, so they can make the ring formation. So O can be reacting with this double bond O, and you can have the OH here. So you have kind of hemiacetal, cyclic hemiacetal formation, right? So that kind of reaction takes place. So this is one of the product, and this product is found to be the major one. Okay. Now in a different way, you can have another reaction. Okay. Now this molecule can abstract, so after irradiation, so it can generate this O-centered radical, which can abstract the proton from this methyl, right? So if you look at, it can generate the radical here. Now this radical, which is which can quickly, since you have a double bond here, it can quickly react at the center to generate the radical over here. Okay, so and you have radical here, that radical can now react with NO to have the initial nitrosyl attachment, and then that can undergo tautomerization to have the oxime formation. Got it? So this way you have a product here. If you look at it is a bit different one. Got it? So you have this product, and now you can do hydrolysis to generate a double bond O. Okay, so if you do hydrolysis, kind of acetic acid water, like weak acid or like that, what it will do, it will be hydrolyzed, and to generate, you will have a double bond O. So you can have the two double bond O successively here. Okay, so this is the reaction we look into if you have the opportunity for abstracting hydrogen in different places. Okay. Now let us look at another example here. If you look at this,
Sir, if we
tell.
sir, if we write if anyone, then it's correct, sir.
What is given based on the thing? Okay, I am telling the whole features. Okay, in the
Yes, sir.
in the
Yes, sir.
exam, maybe I'll be giving a very specific one. Understood?
Yes, sir.
In exam, maybe this methyl, instead of this methyl, I'll give this is lower methyl. Understood? Then it will not abstract from
Yes,
this.
sir.
It will abstract from only here. Okay. If I
Yes,
don't
sir.
give acetic acid as the reagent, acetic acid water, so you don't have the hydroxylation, I mean, don't have the aldehyde formation which will undergo the cyclization in the previous case. Got it? So you will have the only oxime formation. Are you finding? So what is given
Yes, sir.
based on the reaction will be happening. Got it? Another thing is that when you have oxime, you have learned that the oxime can undergo Beckmann rearrangement, right? So under suitable reaction condition, anhydrous acidic condition, okay, like PTSA, paratoluene sulfonic acid, so organic acid which is water free, or you are making a more good living group, like you are using some paratoluene sulfonyl chloride to make a more living group so that you can easily generate the cation, and that way the Beckmann rearrangement can happen. So you just have a look here. For this example, I am bringing that one. So here in this substrate you have again the alkyl nitride here, alkyl nitride here, and if you shine light, what is going to happen? This radical is going to form. So you have NO radical and oxygen center radical. So oxygen center radical will abstract the proton, right? Abstract the hydrogen. Where from it will abstract? This is downwards, so definitely it will abstract from here. Okay, you have an option from here also, but that is upward direction. You have an option from here also, so that are upward direction. These are upward direction, opposite direction. Okay, so opposite direction. So what we see is here, in this case, the oxime will form here. So you have hydrogen abstraction, dot will be generated, that dot will react with the NO, so NO will be combining, then you have the tautomerization, you have the oxime. Got it? So oxime will be there. Now, if you use suppose tosyl chloride, so tosyl chloride, what is its job? It binds with the OH and makes a good living group. So you have the OH here, so that will be converted to a good living group. So TS, so it will be converted to OTS. So OH will be converted to, this is N double bond, okay, and you have OTS. Now OTS is a good living group, so it will try to come out, and then you have the rearrangement. Now in this case, which bond will migrate? The bond in Beckmann rearrangement, you know the migration, right? That happens. So you have opposite to the living group. So this OH is the opposite to this living group. So trans orientation. So we have this bond is trans to this one. Okay. So this is going to migrate. Again, you have another reasoning. When you have the more nucleophilic bond, or the bond having more electron density, that bond can do the migration. Okay. So in this case, this particular bond, okay, which has lot of this connection, right? So you have electron flow. So ultimately, this bond will be highly electron dense over this bond. Okay, got it. So this is more nucleophilic bond. So that is going to be migrating. So it will migrate, and which this OTS will come out, and you have finally the carbocation generation, which will react with the water and generate the amide. So in this way, you know the Beckmann rearrangement uh, happen, which produces the oxime to amide. Okay, so many things are possible. Couple of examples I have shown here. Got it. So let us look at another kind of example. So here, if you look at this substrate, so where from it can abstract the hydrogen, so it will generate this one, oxygen radical, which is upward direction. This methyl is upward direction. So this is going to generate abstract the hydrogen from this methyl, right? So you look at the radical formation here, right? Now the NO can bind here, or what can happen? This methyl, this particular methyl, again upward direction, and this is, if you count from here, 1, 2, 3, 4, methyl carbon 5 and you have a hydrogen 6. Okay, so again it can go 6-member transition state via which the hydrogen transfer process can happen. So 1,5 hydrogen transfer again is happening, and you have the radical formation now is here. Okay, so based on that you have two products. Here you have the initially from here, if the NO is being attached, so you have nitrosyl will be there, and then it will undergo tautomerization to have the oxime. And here the similar way, this stage can undergo recombination and tautomerization to generate the oxime here. Okay, so you have the both possibilities. Okay, you can have this one, you can have that one also. So in this substrate is not that much, I mean, specific one. If you can have this one as downwards, I mean this one is downwards, okay, and this is coming as upwards, then this is coming as upward, then you will have a different scenario. You'll have only exclusively the first product will be the major one. Okay, so this is the way. So we have to look at what is your substrate, what are the possibilities, whether it has a chance to undergo 6-member transition state or not. Okay, so that is the main point here. Now we look into the another reaction which is known as the dipymethane rearrangement. Now this dipymethane rearrangement, from this name itself you can understand di pi. Okay, so what does it indicate? You have 2 pi. Got it? You have 2 pi, di pi. Methane. So the methane is having 2 unsaturation. So how it is, like we call it dichloromethane. Okay, suppose you have dichloromethane. What does it mean? Dichloromethane. Similarly, you have dipymethane. Okay, so you have the CH2 here. So this particular environment we call it as the dipymethane. And when you have this one, this substrate can undergo rearrangement reaction, and that rearrangement is you don't have here n pi star because there is no non-bonding electron, so you have the pi star chemistry. So dipymethane rearrangement is a pi star chemistry. Remember, this is a pi star chemistry. Okay, so how it happens? The dipymethane rearrangement is a photochemical reaction of a molecular entity that contains 2 pi systems. As I am telling, they are separated by a saturated carbon atom. Okay, like this one, or here you see the allylic substituted aromatic ring. So that is also there. So to form an ene or aryl substituted cyclopropane. So what is happening here? During reaction, after reaction, you will have a cyclopropane with a ene, okay, and unsaturation. Okay, so let us look at the rearrangement. Okay, the mechanism wise, the rearrangement reaction formally amounts to a 1 to shift of 1 ene group, okay, in the diene. So you have the diene, so 1 ene will be formally shifted, 1 to shift the aryl or the aryl group, okay, and bond formation between the lateral carbon of the non-migrating moiety. Okay, so let us look at what does it mean. So this is your dipymethane. What product it will generate? Kind of this. Okay, so you have the cyclopropane and you have the 1 ene. Okay, so cyclopropane with 1 ene, that kind of moiety will be forming. Now how it happens? Okay, so in this case, what we see, if you do photolysis, so you have the formation of this initial cyclopropane with 2 radical. Okay, 2 radical. Now these 2 radical can undergo further reaction. So what is going to happen is it can make a double bond here, and this can be opening. Okay, so if it is happening, what we have here, you have a double bond here, right, and that 1 radical, and this is open, so this is another radical, and they can combine. Okay, so they can combine. So what can happen? They can combine. Okay, So we have the product like this. Okay, so this is the product we have. The rearrangement, I mean, this way the reaction takes place. Now here one most important point you have to remember is the reactivity, which is based on the stability of the radical. Okay, which radical is more reactive or the less stable, that will try to first undergo the reaction. So you have the two radical formation, right? Here radical, here radical. Now this particular example, we have identical environment, so you don't have any problem. Anyone can further make the bond and another bond can be clipped. Okay, it doesn't matter. But when we'll have a different types of substrate, then actually you have to be a bit careful. Always remember the radical which is more reactive is difficult to form. The radical, which is more reactive, if it is forming, will undergo reaction first. Okay, so this is the point. These are the points you have to remember. Now let us look at the different examples that will make you more clear about what I just told. Now, example one, you have this particular substrate. Now you tell me you have this center is connected with two pi, right? We can tell this is a dipi methane kind of substrate. Okay, substituted methane. Got it? Now what can we have? We have the radical formation, right? So if the radical is forming, you have this radical, you have this radical, you have this radical, you have this radical. Now tell me, the four radicals are forming, which two radical is going to combine fast? So the phenyl center, these radicals, they are more stable, so they will not undergo reaction easily. Rather, the radical at these two center which are forming, so they are more reactive and they can easily combine. Excuse me. So what we see is that the first combination is happening. So this is the first combination, cyclopropene. Now you have two identical radical. Just a minute. So you have two identical radical. Now, so anyone can further make the bond. So what can happen is, so this is making this double bond. So this will open. So these two radical will be forming, and you have a pi bond relation here. So now they will combine. So they are combining to give you the rearranged product. Any question here?
No, sir.
Clear, right? So let us look at the second example. So what is going to happen? It's not working. So this will form. Okay, so you have the radical generation. So that two will be combining, this two will be combining. You are left with two radicals. Okay, so now tell me, you have the pi bond formation. So which one will make the pi bond? Who can tell? It is A will be opening or B will be opening. So which one will happen more conveniently?
will be opening.
Which one, A or B?
B.
Anybody else? Remember what I told? The radical which is more reactive, that will do reaction. Okay. So here, this radical and this radical, which radical is more reactive?
Right side radical.
This phenyl one or this methyl one? Which one?
Methyl one. Methyl one.
Methyl is more reactive, right? This center is more reactive.
Yes, sir.
That means that will make the double bond.
Oh,
Got it?
yes, sir. Open this A bond.
A bond will open. Good. So that is
Yes.
making double bond. So A has opened and you have the generation. If A is opening, so you have the generation radical there, and now they are combining. Is it clear to you?
Yes, sir.
Yes.
Okay. Now let me tell you a bit more difficult example. So you know the berylline, right? This structure. Have you seen this structure earlier? This structure have you seen earlier?
No, sir.
Hey, why you have not seen?
Yes, sir.
Where,
Yes, sir.
where you have seen?
I maybe forget, sir.
This one I discussed in the first semester when I was
First semester in acid.
no, not acid.
Acid,
When
yes.
I was discussing the aromaticity.
Yes, sir. Aromatic.
Yes, it will be there. Okay. So this substrate, again you see two pi bond, they are connected with one sp3 carbon, right? This is sp3 carbon. Similarly, sp3 carbon. So they are connected, two pi bonds, they are connected with sp3 carbon. That means this one also can undergo dipymethane rearrangement to give you the product under light irradiation. So what can happen is, if you irradiate, what is going to happen? Uh, you can expect that two radical formation, right? Getting? Now, these two radical, they can combine, so you have this structure. Got it? Till now it is okay? You are getting this structure. Is it okay to you?
Yes, sir.
Now, what you have
Sir,
radical.
once more time.
So this structure, this is a double bond, this is a double bond, you have double bond here, right? They are connected
Yes,
with
sir.
sp3 center. So that two double bond will be initially making the radical. So you have the radical here, you have radical here, radical here, radical here. Now these two center, they can connect. So that is connecting. So you have a three-membered ring here. What you are left with? A radical here, a radical here, a radical here, a radical at this center, right? So that two radical, a radical here, a radical at this center. So till now it is okay, right?
Yes,
Yes,
sir.
sir.
Now what can happen is, you have the dipymethane rearrangement. So what we have seen is the reopening of the cyclopropane ring. How it is opening? Whatever radical has formed, among that radical, which radical is more reactive, that radical should undergo reaction, right? So here in this case, if you look at these two radicals, they are almost identical. Okay, almost identical radical. You have this radical, which is, I mean, the homoallylic to this double bond. Again, this radical is, you have homoallylic to this. Okay, so in this case, what we see is you have just the one of the radical is making the pi bond. So if this is making a pi bond, what is going to happen? This is going to open. Now it can, you can think, sir, I can take this can open. Okay. What I'm telling is, no, it will open this one to have a radical here, because that is the allylic position. Are you getting? So double bond you have this radical generation. So allylic position radical generation is more stable. So that's why that will be opening. Get it? So you are getting this structure. Are you following?
Yes, sir.
So this structure will be there. Now what can happen? This structure is nothing but just the same of this one. If you give the numbering, you'll understand. So you have this, if you look at, this is 1, 2, 3, 4, 5. Okay. So this is like you have. So what I was telling you is the similarity of these two structure, right? So that two structure are the same structure. If you count that one, if I give the numbering, so this 1, 2, 3, 4, 5. So this is the same. You have the three bond connected. So this is the one. So you have 2, 3, 4, 5. So 5 you have the radical. So 5 you have the radical. Okay. And then you have the other radical here, allylic position. So allylic position. Okay. So these are two structure. Now what can happen is these two structure, this radical can combine, this radical can combine, and you have this one. Okay. You have this structure. So this one we call it as the semi-bulvalin. Okay, that rearrangement from here to here, that transformation is happening if you shine light. Okay, and this is the example of the dipi methane rearrangement reaction. Okay, this is a bit complicated one, a bit difficult, but in the exams generally we find the the reactions like this. Okay, that too. Okay, so let us come to another type of reactions, which is the chemistry of arenes under light. Okay, now arene, when you talk about, it is the same substrate where you have only the pi bonds, right? So when you are talking about the photochemistry of arene, we are actually talking about the pi star transition. Okay, pi star transition. Now the benzene is the one of the simplest one, arene, and benzene and its substituted benzene generally undergoes valence isomerization by irradiation. Selective excitation into S1 state gives preferentially the meta and ortho product, while the excitation of the S2 state gives para bonded products by valence isomerization. So these processes are described by biradical intermediate for, the biradical intermediate formations. Okay, so let us look at how it happens. Now the benzene, if you sign with 250, I mean the this is the general wavelength I'm talking about. Okay. Now specifically, if you sign with 205, what you can have the excess of S2 excited singlet state. If you sign with lower wavelength, the higher wavelength of lower energy, 254 nanometer, you'll be having S1 transition state. Okay, that excited state you'll be getting. Okay, now in case of S2, what has been found is that the 1,2 or 1,4 biradical forms. Okay, 1,2 or 1,4 biradical formation. Biradical formation. Okay. In case of S1, what we see is that 1,3 biradical formation. Okay, 1,3 biradical formation. Okay, biradical formation. Okay, so these are the two different uh, ways of forming biradical from the benzene. Now, if you do the S1 excitation, what you can have as a product is that you have the initial 1,3 biradical formation takes place. Okay. Now this one you can think like you have the radical here, you have the radical here, you have the radical here, you have the radical here. Now these two radical, they can combine. Got it? So if I write in this way, you will understand. So I have radical here, I have radical here, I have radical here, I have radical here. Okay. So these two radical are combining and you have the two radicals here. So that is the thing. Okay. So it's happening. Now this one, what further can happen? You have hydrogen here. So that hydrogen radical abstraction is taking place. So you have radical generation here. Okay. So that is happening. You have radical generation here. Got it? And okay, so this is allylic position we have to take. So this is I did wrong one. Opposite one will be the more preferable. Okay, the opposite is the allylic one. So what can happen is, if you look at here, you have hydrogen here. Okay, so this radical can abstract this hydrogen. It will generate a allylic radical. Okay, so this is the allylic radical here. Now this is the same, it is generating this allylic radical. So this allylic radical, you have 1,3 position. Now it can make a double bond here. So it can be cleaved and you have a double bond. So this is a double bond and you have a double bond here. So what you can think like this is cleaving this way. Okay, this is cleaving this way. So this means I can write in this way. You have 5-membered ring, double bond. You have radical here, you have CH2 radical here, you have initially radical here, you have radical here. So this is kind of double bond formation, and that is double bond formation. So what you have here, you have this structure is gaining. Okay, this structure is gaining. We call this is fulvene. So or fulvene is there. So this structure is happening. Now if you do S2 excitation, what can happen? Okay, what can happen? So S2 excitation, as I told, it will generate 1,4 or 1,2 biradical. So this is 1,4 biradical, which can form the 1,2 biradical also. So this way it will make dimer benzene. Okay, so these two will be combining and you have the dimer benzene. Okay, dimer benzene. Now let us look at the dimer benzene, what it can do further. So you have 2 plus 2 cycloaddition under photochemical conditions. So you have two double bonds, so they can undergo 2 plus 2 cycloaddition reaction. Okay, so you have 2 plus 2 cycloaddition reaction and you will be generating this as your substrate. Now let us look at how this knowledge can help to understand the isomerization of substituted benzene. Okay, so let us look at the ortho to meta rearrangement reaction. So this is the ortho compounds. You have 2R here at the ortho position. Okay, now this, if you do excitation at S2, okay, so what is going to happen? It is going to make dimer benzene first. Okay, now this dimer benzene is going to 2 plus 2 cycloaddition reaction, so it will make this one. Now here in this case, if you look at, I'll give the different color. Okay, so you have a 4-membered ring, right? So this is the 4-membered ring. So what can happen is this 4-membered ring can reopen. Okay, it can reopen. So this is coming here and this is coming here. So you have a double bond here, you have a double bond here, that too open. So this is going to be the structure. Okay, if that this bond is breaking and this bond is breaking, and here you are having the two double bonds, so you are having these two double bond and open. So now this one you can rearrange and you can have, this is the structure which you can make it in the benzene form, and that is one the two carbon that has been separated. Okay, so the reopening of this one is happening. So this is again the double bond formation. So it is coming here, it is opening. So you have 6-membered ring, and the benzene is getting its structure. So you have the two are, they are now at the meta position. Okay, so what is happening here? You have the consecutive 2+2 cycloaddition reaction. Again, that the 4-membered ring is being opening. Okay, so that process are happening, and finally the more the formation of ortho to meta rearrangement product is happening. Okay, so similarly,
Sir,
yes, tell.
sir, this side four member ring is opening. Can I opening this side, sir? 1, 6, 5, 4 position.
This position, this side you are talking,
No, sir.
the upper one you are talking
Yes, sir.
here.
Yes, sir.
Yeah, no problem.
Yes, sir.
You
Yes, sir.
can try with this one. Okay, and you will see what product you are getting. Understood? You can try
Yes,
this
sir.
one and you can find out what product you are getting. Got it? So ultimately you do that one, and again you go through the whole step and see what product, whether you are achieving this one or you are achieving something else. Okay, that you can try and see what is happening. Okay, so now let us look at another example where you see the ortho to para rearrangement, and I think you will get the answer here. Okay, so what you see here is that you have the ortho compound, your benzene formation. If you do sign light and this is happening, then you are having 2+2 cycloaddition. Okay, and this is your 2+2 no, product after 2+2 cycloaddition. Now you look at what bond has been opened. What you are telling, it is this one, right? Are you getting or not?
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Yes. So you have this probability too, and this is opening, and what you see is that these double bond are forming, and if you count the number, your 2R will be, I mean, the para position to each other. If you further proceed, and you will have para product. Okay. So you have two probabilities. Based on the situation, the ring opening will happen, and you will have the product formation. Got it? So these are in a coincided way. I just I just told you have a vast topic. This one, if you are more interested, we'll have more discussion on this one, because a lot of reactions are there. I'm just telling you how the orthopara or orthometa orientation happens, and these are possible via photochemical route. Okay, so this is the message I want to convey. And what you do, you try to do the practice of whatever examples I have shown, and I hope this will be quite beneficial. Since we are not getting that much time to interact to each other, I don't know how much helping this one to you, but if you can spend some time to read and try to understand, I hope these examples are quite interesting and can be beneficial in your different exams. Okay, so I'm stopping here. I'll prefer you to go through and interact and clear your doubts when you are coming to the campus. Okay, so anybody is having anything, just quickly in 1 minute. Quickly in 1 minute. Okay, then I'm stopping here. I'll be posting this one later on, and you just go through. So thanks for attending today's class. Thank you.
Thank you, sir.
Sir.
Thank you, sir.
Oh, why it is not ending?